Hey guys, so today we're going to be going over the two comparison tests for series, which is the direct comparison and the limit comparison. So for each one, I'm going to do an easy one and a hard one, and we'll go step by step, and I'll show you exactly how I'm going about it. So first question, we're going to do the direct comparison test first. So it's a series of 1 over n squared plus 5. Now, the first thing I notice is that this kind of looks like a p-series, right? The only problem is this plus 5, right? If this plus 5 wasn't here, then this would be an easy question. We just use p-series. But this plus 5 is here. Now, for comparison tests, or for any questions that kind of look similar to another type of series, that's when you use these two comparison tests. Now, like we said, this looks really close to 1 over n squared. So that's what we're directly comparing it to. So, we're going to choose 1 over n squared as our known series. So 1 over n squared, that's our known series. Now, what do we know about this? Well, we know it converges, right? Converges. Why? It converges by p series. P equals 2, which is bigger than 1, right? And if you don't know what p series are, I have a video on that. But we know this series in particular converges. Now, there's a kind of like a theorem. 1 over n squared plus 5 is obviously less than n squared, 1 over n squared. Why? Well, because we're making I can't talk. We're making the denominator bigger. So 1 over 10 is bigger than 1 over 15, right? So we know that 1 over n squared plus 5 is smaller than 1 over n squared. Now, we know this inequality is true, but how does that help us? Well, there's kind of like a little bit of a theorem. We know 1 over n squared converges. We know this converges. Since 1 over n squared plus 5 is less than that, it also converges. So, if anything is less than a converging series, it also converges. Now, if anything is bigger than a diverging series, it diverges. But here's kind of the nuance. If something is less than a divergent series, we don't know what it does. And if something is more than a convergent series, we don't know what it does. You have to have those two kind of endpoints. So, let me write this down for you guys. If series is smaller than converging series, that equals convergence. I'll just write C for convergence. And then if series is bigger than a diverging series, then it diverges. And that kind of makes sense, right? As it's getting bigger, it's you're more likely to diverge. So this is like the main kind of rule in both comparison tests. So now we can write our answer. Especially on the AP exam, you have to write like each little thing. So since and I might speed this up for you guys. N equals 1 over n squared is bigger than. Okay, so boom. This is basically what you'd write on the AP exam. This thing I circled in red. This blue stuff, let me just erase it so it's a little bit neater. But make sure you remember that blue stuff. That blue stuff is important. But that thing in the box is usually what you'd have to write for your AP exam because they're really picky on how you justify your problem. Oops, sorry, wait, this should be 0, this should be 0. They should all be the same, okay? So, it's not bad, right? You just have to get used to figuring out what you're going to compare it to. So now, let's go to our next example. So, the series 1 over n minus root n. Again, we need something to compare it to. Well, the easiest way for me to think about this is, let's pretend you're putting in a huge number. This is the same thing as 1 over n minus n to the 1/2. At huge numbers, right? Let's say at 100 billion, million, quadrillion, whatever. This n is going to overpower this n to the 1/2 any day. So, at large n's, this negative root n becomes negligible. So what I'm going to compare it to is I'm going to make my comparing series 1 over n. Okay? So usually, I don't want to say in all cases, but most cases you kind of get rid of the smallest term, especially in the denominator. But that's kind of a little trick. But I don't know. I wouldn't say that, you'd use that every time. So now let's look at this. This is a harmonic series or a p series. And we know this diverges because I'll just use p series. So p series diverges y because p equals 1, right? So p series diverge if p is less than or equal to 1. So now let's write our thing. Well, first let's compare the two values. How do these compare? Obviously 1 over n, 1 over 1 minus n minus, oh my god, I can't talk. 1 over n minus root n is bigger, right? Because you're subtracting something from the denominator, you're making the denominator smaller. Now, remember what I said before. If we know this diverges, and since this in pink is bigger than the diverging series, it also diverges, right? That's that kind of thing I wrote in blue in this here. I erased it here, but it was there. I swear it was there. So 1 over n minus root n is bigger than 1 over n, and 1 over n is a known divergent series. So, since 1 over n minus root n is bigger than a known divergent series, it also diverges. So that's basically what I'm going to write down. Since n equals 1 over n, you should write this part, otherwise you might have to write it in your explanation. So I just, since 1 over root n diverges, I'll speed this up for you guys again. Okay, so this whole like orange circle is pretty much what I'd write on my paper. This could be mental math, but it's always more helpful to write it down. But this these words are the most important. Since 1 over n diverges and 1 over n minus root n is bigger than a known divergent series, then this bigger series also diverges. All right, so it's not bad. It just takes a little bit of practice of getting used to what you're going to compare it to. That's, I think, the hardest part, and then figuring out like the inequality. Because let's just say for example, this was n, I don't know, to the 100, and this was just n. So something like this. And this is no, sorry, this is root n. Okay, there we go. This is root n. 1 over root n is bigger than 1 over n, right? And 1 over n also diverges by p series. We can't conclude anything about 1 over n. Let's say just we don't know what it is, right? We can't conclude. This 1 over n is smaller than a divergent series. It could be divergent, but it could also be convergent. So, you can only determine in direct comparison if something is divergent if it's bigger than your known divergent series or if it's smaller than your known convergent series. If it's smaller than a divergent series, you don't know anything. And if it's bigger than a convergent series, you don't know anything. You're going to need to use another test. Which is why I usually I prefer the limit comparison. But I mean, oh gosh, everybody has their own preferences. Let me fix that. All right, there we go. All right, so now let's go on to limit comparison. So limit comparison. So you take the limit of as n goes to infinity of an over bn. An is the series they give you, series given, and then bn your comparison. All right, so you just divide them. Now, if this limit converges, then the series an and the series bn either both converge or diverge. A lot of people make a big mistake, right? They just look at the limit and say, "Oh, this limit converges," and so then the whole thing converges. No, your your limit converging doesn't mean anything. You actually have to test whether an or bn diverge or converge. All right. So the limit convergent, like if this limit converges, that kind of gives you the green light to go ahead and figure out whether your comparison converges or diverges. So let's go over that. So uh, the series from 1 to infinity, 1 over n squared plus 3n. Now remember what I said. In a lot of these, I like to just look at the biggest term. So for me, that's always obviously n squared. Right, so again, why do I do that? Well, let's say we take a big number like 100 million. This 3n becomes negligible, right? 100 million squared is so much bigger than 300 million that 300 million barely makes, it's like a drop in the ocean. So our comparison is going to be, so our bn is going to be 1 over n squared, and then our an is what they gave us, so an equals 1 over n squared plus 3n. So now let's take the limit. So the limit as n goes to infinity of an, so 1 over n squared plus 3n over 1 over n squared. Now, let's do this. So this becomes n squared over n squared plus 3, oops, I forgot the limit sign. Don't ever forget the limit sign. Limit as n goes to infinity, n squared over n squared plus 3n. And now we can use our, however you guys like to solve limits. So, how do we do that? Well, if we plug in infinity to the denominator and the numerator, we get infinity over infinity. That gives us the green light for L'Hopital. L'Hopital. So now we take the L'Hopital's rule, right? We just take the derivative of the top and the bottom. So the limit as n goes to infinity of 2n over 2n plus 3. Again, we get infinity over infinity. So we're going to use L'Hopital again. So it's the limit as n goes to infinity of 2 over 2, which is just 1. Now, since this limit converges, now we can say that an or bn either both converge or both diverge, right? That's what we said. If this limit converges, then an and bn either both converge or diverge. So I chose 1 over n squared because, right, we said the negligible 3n, but also because it's a super easy limit, or super easy series to test, right? This is a p series again, p series, and p is bigger than 2, or no, sorry, p equals 2, which is bigger than 1, which means it converges. So now you basically say, since I don't have enough space, shoot. I'll just write it super small. So we say, since the limit, you have to write the whole limit, but I'm too lazy. Limit converges and bn equals whatever 1 over n squared converges, then an also converges. You'd have to write like the actual series inside for an and bn, but I don't have enough space. So, but that's basically how it goes, right? And this is the limit comparison test. A lot of the times I like to use this one because it's low-key a pain to do all this inequality stuff. So limit comparison is usually the way I like to go, but I mean everybody has their own preferences. So last question. So this series n squared plus 1 over n cubed plus 7. Now, this one's a little bit tricky, but again, just pretend that you're having a huge number as n, 100 million. 100 million squared plus 1, this 1 becomes irrelevant. And the 100 million cubed plus 7, that 7 becomes irrelevant. So I'm going to compare it to my bn is going to be n squared over n cubed. Most of the time, like if you have questions like this, like just cover up the constants, and that's your comparison. Not every time, but I'd say like 95% of the time. And this simplifies down to 1 over n, and then an is their limit that they, or their series that they gave us. So now let's take the limit. As n goes to infinity of an, so n squared plus 1 over n cubed plus 7 over n squared over n cubed equals limit as n goes to infinity of n squared plus 1 times n cubed over n cubed plus 7 over n squared. So now this cancels with the numerator, so this becomes just n on the numerator. And we get this. Now we could use L'Hopital. We can keep just using L'Hopital over and over and over again. So let's just do that, and I'll speed it up. I'm sure you guys know how to do L'Hopital, right? N cubed plus n over n cubed plus 7. Now, this is all I did here was just simplify this out. So now we can use L'Hopital because it's going to be infinity over infinity. L'Hopital. So limit as n goes to infinity of 3n squared plus 1 over 3n squared. Again, infinity over infinity. We get 1. Eventually, we're going to get 1, right? Because it's going to be 6n, 6n, and then eventually 6 over, 6. 6 over 6, which is 1. If you guys don't believe me, you can always do it out. So now, since this converges, now we can test whether bn or an either both converge or diverge. Again, I chose bn. 1 over n is super easy. This is harmonic series, or a p series, and the p is not bigger than 1, so diverges. Now, since the limit, and you have to write this, limit converged and bn is divergent, then an is also divergent. And boom, that's it. It's not so hard once you get the hang of it. Right, you kind of get into a groove. You know, it's a little bit tricky, I guess, to kind of figure out what you're comparing it to, but all that just comes with practice. But anyway, I hope you guys learned. That's pretty much all you guys need to know for limit and direct comparison tests. But yeah, I hope you guys enjoy this video. If you have any questions, leave them in the comments. If you have any suggestions for me to improve my videos, leave them in the comments. Like, subscribe. I'd really appreciate it. And thank you guys so much for watching.